of South Dakota, Wisconsin, UP, all of Illinois, all of Iowa, and half of Missouri. They concentrate basically on automotive and aerospace. So a lot of the tools I'm going to show you is surround with that. They actually go well with the machine tools that are out there too. So with that said, let's start off with the video. So I turn my clicker on.
In 60 seconds, you can eat 2 small cheeseburgers, read a comic strip, write a super short email, or you can get an idea of how to improve your production. With Sandvik Coromant, 60 seconds, starting now. The world is changing fast. Urbanization is growing. Population is aging. Climate is changing. Digital is happening. New materials are coming every day. Change is not easy. We need to lower emissions. Engines are downsizing. You need to craft new materials. You need to reduce cost per part without reducing quality. You compete globally. On top of that, you need to machine a component that is a geometric nightmare. Tough work. Together, we can take your production to the next level with dedicated milling cutters, with industry-leading anti-vibration tools, with unique high-precision coolant solutions. And we have the expertise and experience to map processes that will thrust you forward. We'd like to talk to you about component solutions.
Welcome everybody. This is going to be a presentation on machining economics, a short presentation on that, pasty vein technology, and all these tools we have out there by our booth. So if you want to take a little close-up of the tools itself, you're welcome to. But I mean, some of the customers' challenges, right? I mean, here we've got a big bird's nest. I mean, nothing could be worse than that. You know, poor chip control, long cycle times, inconsistent tool life. You know, between the machine tool and the cutting tools, I think we have some solutions. So let's go ahead and take a look at another solution here. In titanium, a lot of drag beams for the aerospace industry are made out of titanium. So having tooling solutions for that works well with a very good machine. A lot of new CAM softwares offer the high-speed side machining in their version of it, whether it be volume mill or some of the other ones that are out there. Utilize your whole axial length of cut of the end mill with very shallow radial cuts. You go very fast. The best thing for the tool to maintain the same chip thickness or your hex wherever you are in the part. And there's also power milling too, where you still maintain the same chip thickness, but you also maintain the same radial engagement. Now, titanium machining, it's not an easy material to machine, but you can see that you need the right tools for that. Versatile style tools don't work too well. That should make it one small, inexpensive part. But parts like this over here are very expensive, so you want to put best foot forward with a very good machine. Tool and tool itself. Or take a look at a blade disc, right, for turbine engines. I mean, there's a big challenge there to reach down between these fins. I mean, sometimes you see in the news some turbine engines that have blown up, and you see pieces of the disc of titanium and ink, they're all blown up, laying all over the place. So you do need to have the right equipment. You've got to be capable of running as fast as the tool itself can, and obviously the software too. All right, touch and base before going to the end mills itself, machine economy, right? So we have this pyramid over here, I should say pyramid, the column. So if I decrease the cost of the insert or the tool to you, you're basically saving only 1% per component. If I go ahead and double the tool life for you, which some people need that to keep up with maybe a bottleneck area, which is fine too, but you're really only saving 1% of that. Now go ahead, if I increase your productivity by 20%, now you get a nice savings of 15% per component. So when you're looking and analyzing maybe a job or a brand new job, think of getting the right tools for the right materials and the right machine tool for that too. So tooling normally is going to be 3 to 5%. In the aerospace industry or materials where tough machine and tough machining applications, it'll be a little higher than that. But this is a general rule of thumb for machining economics. So your overhead, 22%, labor is 31%, then you got machinery to put it about 27%, and the workpiece material, that can fluctuate also, and that's that gray area there. Let's take a little closer look as we analyze the cost per component. So in this pie chart, you have variable costs. These will always change. Price increases. But your machinery, once you paid for it, there it's about 27% labor and the building and admin. Those don't change. So no matter what you do, you have to decrease cycle time in order for all three of these to change. So we'll go ahead and move that to the side and take a little closer look at it. So shop spends $10,000 to make 1,000 parts, and it costs $10 a part to make. All right. So variable cost today is 30 cents per part. Workpiece material costs $1.70, and you got the fixed costs, which comes out to $10 per part. That's how we calculate out the machining economics for a part. So go ahead and decrease the cost of the tool itself. So I decreased the 30 cents down to 21 cents because we gave you a bargain on those cutting tools for whatever reason. But your workpiece material still doesn't change. You still have to pay $1.70 for that workpiece material, and your fixed costs, they don't change it either. You haven't done anything to improve on that. So now you save yourself a whole 9 cents per component. When you go ahead and double your tool life, 50% longer, well, now I'm only paying 20% versus 30% if I used to pay for my tool. But my workpiece material is still at $1.70, and my fixed costs are still the same. I haven't done anything to reduce the cost of that there until I start messing around with cycle time. I get more soluble parts at the end of the day. Sometimes it ain't about cycle time, it's about maybe getting a right balance between tool life and cycle time to get those parts at the end of the day. Less operator intervention. All right, so now we go ahead, we analyze that. We did a 20% increase in productivity, and there we got, ooh, and when actually my cost for tooling went up. Why? Well, because I used more inserts to get the parts out quicker, all right? And then if I look at my fixed cost, that went down to $2.16, $2.40, and $1.76, because now I'm making more parts per hour, all right? That reduces the cost. And now I save myself, it went down to $8.55 per part, so we got a much lower cost. I saved myself 15%. It's kind of general rule of the average cost. We did take surveys on what the customer had done, and be surprised in a lot of cases where customers' productivity increase was only like 25%. And not productivity increase, but their output was only 25% because machines were down, broken, didn't select the right tools or right machine tool for the application or anything. But here's a machining module. All right, let's take a look at another example here. I'm going to jump to PCB vane technology, actually. All right, this PCB vane technology is unique to Sandvik Coromant, and this is where we basically, if you ever seen an old Superman episode a long time ago, maybe for some of us older guys, where he was going to give Lois Lane a diamond. He took a piece of coal, and with heat and pressure, he squeezed it, and he gave Lois Lane a nice sized diamond. Well, basically, it's doing the same thing when you go with synthetic diamonds here. Through heat and pressure, you can make diamond. Once you take the diamond part, it all comes out carbon. All right. So it goes in this machine tool. After it comes out of the machine tool, we take this nib, and you can see these nibs at our booth over there, and a lot of the tools. These tools actually go down to 9,000ths in diameter. So we have PCB vane. I'll show you why it works out very well for us as soon as this video finishes. But after the nib is done, we go ahead and braze it onto whatever shank it might be. Aerospace industry uses a lot of, especially for the ADU units, the automatic drilling units that you drill by hand. Those are either quick release or the threaded with an M6 or M8. All right. So step one, we take a carbide blank, we slot it, We used to use grinders to put the slots in there, now we do lasers. With a laser, you can go anywhere you want. You can make any kind of point, whether it's a drill, reamer, or an end mill. All right? So now you go ahead, whatever configuration you want to do over there, then you take it, you put it in the machine, and you put it in the cup, put the powder in there. There's several different grades of powder to tailor towards your material that you're cutting. Like high silicon content will use more of a certain powder than the other powder. I'm talking about PCD powder it is. So it goes in the machine and through heat and pressure, 2,700 degrees Fahrenheit at 876,000 PSI. You squeeze it together and now you guys have a diamond, almost. You still have to braze it onto the tool and then finally you go ahead and qualify the whole tool itself. So we'll go ahead and take a little closer look at that. And let's see what the nibs look like. This might be, say, a 5/8 or 16 millimeter. So we go ahead and we grind slots in it. So this, in this case, it's going to be a drill. And we pour a certain PCD powder. There's 6 different styles. Depends on the silicon content, aluminum, or maybe you're running some carbon fiber reinforced plastic, or maybe you're doing some stacked materials which has aluminum, carbon fiber reinforced plastic, and titanium. A lot of these airplanes' wings, like the 777X down in Boeing St. Louis, they have this stacked material, along with a lightning shield, which is basically a brass shield over it. So we go ahead and fill up PCD powder, and we go ahead with a production line over there. We put it in this cube. If you see that cube that was inside the machine tool itself, put a disc on top of it. That's a proprietary cube, by the way. And we go ahead and we squeeze it to the 876,000 PSI, 27 degrees Fahrenheit, and then you have a crude cube that looks something like this. We go ahead and break it apart, but we need to know where that vein is, like a vein of gold in a mountain or something. This is actually diamond. So what we got to do there then is we have to qualify it to find out where that vein is at. So now we have to orientate that the grinders itself. All right. So here you have different examples and reamer over here. And then we go ahead and we braze it onto whatever shank is required. These are all special tools. We go down from 9 thousandths in diameter up to 16 millimeter or 5/8 or 630 thousandths. Put on any kind of shank you want. And after we do that, then we go ahead and we qualify it to that, whether it has flutes, straight flutes, high helix flutes and all that. For how well this works, you do need a catalyst of cobalt to help bind everything together, similar to how carbide is made. I wish cubic boron nitrate was like that too, but we can't press it hard enough so it becomes homogeneous as one piece. So PCD, polycrystalline diamond, is a composite material made up of crystals of synthetic monocrystalline diamond between 2 microns to 60 microns. Depends on the application. All right. Then it goes into a sintering process. And look at it chemically. We go ahead and we bond those two together with cobalt, and we squeeze it, heat it, and now we have a man-made diamond. As a matter of fact, if you've seen an episode of Breaking Bad, episode 2, season 1, he talks about the invention of PCD vein diamond. If we got time at the end of the day, not the end of the day, but at the end of this hour, we'll do something. But PCD diamond is 2.7 harder than carbide is, right? Right? It has a low thermal expansion, so no matter how hard it gets, it's not going to shrink or grow in any reason. And low coefficients can be nice and slippery, right? And great manipulation. So you can see in this graph over here, this noob scale, that is much harder. I wish we could use diamond in steel. It would have worked out great for hard parts. But diamond is also used in carbide. Carbide dies in the green state. You know, we could do 64. Not 64. Up to 90 on the Vickers scale. We can use PC diamond or turning, milling, or drilling. A lot of companies who do carbide dies, they have to drill. They use our drills because the vein comes all the way to the point. And I'll show you that when we get a little closer. All right. As you can see over here, normally a tip drill will be 2 braze points. But unfortunately, you can't take these 2 braze points and put them together. So you make a nice, very close point to it. Don't work that way. So all our competitor drills will have a piece of carbide. Once the carbide wears a little bit, it starts to wonk. And then you start losing your whole qualities like position, surface finish, cylindricity, where the PCD vein diamond goes all the way to the tip. And that's the magic behind this over here. It doesn't wear out. Just in comparison, let's say we run in a carbide drill in some material, and I get 100 parts. All right. So I decided to go to a coated drill, and that might give me 125 parts. All right. So then I decided to go to a true CVD PCD diamond. It takes about 20 days to grow onto the drill. All right. So there's a big cost factor in that because of the whole process, and that cost of that tool is about as much as a PCD vein. But unfortunately, with that PCD coated carbide, true CVD PCD, you can't resharpen those. You have to throw them out and get new ones. Where here, you can go to 3 to 5 sharpens or more. So I go to a true CVD coated, PCD CVD coated drill, and that gives me, say, 500 parts. All right. And then when I go to a true diamond, the vein technology, I could get something like 10,000 parts. I mean, these tools stay in there all year, and they're expensive, but in comparison to the CVD style, they're not that far off, especially when you use 3 to 5 regrinds on that. That really amortizes the cost of that tool. Now, it's a lot cheaper than using anything else. But if you're running high production, all right, you need something that's going to be lasting that long, because if an operator's sitting there, he's always changing tools, well, there's always that margin of error. But the longer that tool can stay in there, in the cut, less handling the operator, the less chances for any mistakes to happen, especially maybe touching off the tool, breaking it. So these last a very long time in comparison to all the other ones there. So advantages, complex geometry versus anything else. PCD wafers, typical drills, they're just brazed on there, so you don't have no rake to it. Where we could provide a rake in any shape or form. Whether it could be a tree flute, could be a reamer, even could be an end mill. End mills will have a certain length to diameter ratio on that, and it's not very big because the machine that I'm talking about is about half the size of this room. All right, so it's to do a longer length of cut, APMX or flute length you want, it'll be twice that big, and it's almost unheard of to make anything like that. And there's really no use for anything much bigger than that. All right, allows customization of engineered solutions, but the limitation obviously is the length and thickness of the veins itself. I haven't found any limitation where the aerospace industry didn't like it, or the automotive industry didn't like it. As a matter of fact, out here in Minnesota, there's companies who use PCD vein technology in the boring bar form to do heart valves out of platinum. The name eludes me, I'm sure, Dan, you know. All right, so we'll continue on from here. Any questions so far about PCD vein technology?
Do you guys use coolant with this? I mean, through coolant?
Yes, yes. If I could run faster. If your carbide tool is already optimized, more than likely I cannot go any faster. But I'm going to have less burrs on exit, if it's an exit hole. I'm going to have better surface finish, hole quality, positioning from one hole to another, very important in aerospace and automotive industry. So all my hole qualities get so much better, and they last for a long time. When a drill fails at 9,999, it goes. Once the size changes, that's when you'll see that, all right, it's time to change it. But the size will not change unless there's a machine tool or maybe there's something with a cold or something like that. But more, 99% of the time, the size will not change. And when it does, that means it's already wore out, time to change it.
What is, do you include the regrinds on that 10,000 number?
Yes. Oh, no, not
So
at all.
it could become 30,000?
Yes, absolutely. So let's say it's half-inch drill. Half-inch drill, uncoated for 100 parts. We'll get somebody, I mean, obviously there's a big difference in price range. You can go to, like some of our competitors have general purpose drills, but we'll choose the top 3 good drills, all right? So a half-inch drill, 3 times diameter, we'll say $100, all right? Then you get tin coated, $105, because there's not much more than that. And then you go to true CVD coating, now that jumps up to some around $500. Where now the half-inch, 3 times diameter is going to be somewhere around $600 to $700. But I cannot regrind this true CVD PCD drill. I could get.
In percentage, what is the cost of the regrind?
It's about 25%. The more complex the tool is, the more expensive. Now, it is only the front end of the drill. All right, if you got a chamfer, then I have to do braze. There's a certain point where I cannot go past over there. You'll see some of those nibs and those tools out there by our booth over there. But the front end is going to be, that's where the busy end is most of the time, in any combination tool. Was it drill chamfer, drill ream, dreamer, so to speak, and any kind of counterboard tools. All right. So with the invention of laser technology, we have 2 lasers that are in-house, where now we can go ahead and laser off cutting edges. And it's going to be a lot more uniform than grinding. Grinding, you might not see it in your tools because it feels pretty good, but under a microscope, grinding actually takes away particles from the cutting edge. All right? And it could be very inconsistent. Laser does not do that. So you're going to have a more consistent laser edge in any shape or form. Where grinding, you got to put the form into the wheel itself or not. All right. So you can see the difference right there. And once you have a consistent tool, a consistent cutting edge, you're going to have some kind of consistency at your production. It's very, very important to have that. To make sure that, okay, if I'm going to buy Hank one of your expensive tools, I want to be able to get 10,000 parts out of the deal. All right. I want to get 10,000 parts all the time. Absolutely, you will. Oops. And some of the other tools that were small tools, like the company out here in Minnesota, does heart valves and platinum, small diameter, 9,000, 15,000 diameter drills. This technology goes on something that small. We got some of those, we got a 15,000 drill over there. Believe it or not, it has that fitting technology on there. There is because of laser technology, we don't have to rely on this elderly person that's close to retirement, because he's the only one who knows how to do all these micro tools. So with the laser technology, because he actually, to make 10 drills, he's got to make 20 samples first. Some of them break, especially when they're small diameter like that. But with laser technology, there's no tool pressure at all on the part. So now you put 10 blanks off the shelf, you make 10, providing there's no dimensional mistakes. You can make 10 drills, or 10 boring bars, or 10 reamers, or 10 end mills. All right, so some of the other things, the final product, straight flute, helical flute, reamers, end mills, all right, small diameter stuff over there. This is vein technology. Patents ran out for the last 10 years. It works, and nobody has been able to mimic it. The best part about this is the whole quality you get from it, because that PCD vein goes all the way to the tip of the tool. If you stop by the booth over there, you'll see it. All right. The range, all right. Here we say comfortably in a big production area, 0.4 millimeters, basically 12 thousandths almost. All right. And the maximum is 16 millimeter. After that, we have to go to a braze. But this is actually the beginning, the front end of the tool itself. All right. So we'll go on to something else over here. Let's go to some more titanium machining. This is a replaceable head, Coromant 316, what we use. It's got a screw-on head there. It does have a unique collet to it. It's a CF 393 CF collet that no matter what the centrifugal force is, the coolant goes straight down the shank of the tool. And you notice that when the coolant starts going down there. A lot of times, if you don't use this type of collet, whether it's an ER collet or a hydraulic collet, you get coolant that sprays out in the fan, and it's not even touching the tool anymore. So it doesn't do any good other than washing some of the chips away. But in this example over here, we're doing something that might look like a drag beam or a titanium component for the aerospace industry, where we're utilizing high-feed side machining techniques, right, and using a true high-feed side milling type of tool. Now this tool, if it does a side, it's actually going to helically interpolate a triangular pocket, which is an example of a typical aerospace frame pocket. And we always run it wet. So the 10 millimeters sticking out that far, which I would presume is somewhere around 7 to 8 inches. The high-feed side milling, that is the way to go. There's no place for power milling, but high-feed side milling. Parts are getting more near net shape, not in aerospace, but maybe in automotive, so high-feed side machining could be a benefit there. a lot of components for the aerospace industry, you have to start with a billet. You can't use near net shapes or anything because of fracturing. It's kind of hard to see what up close. We do the best we can in that camera and all that. But it's going to do the same thing on the other side over there too. So I'll go ahead and fast forward from that because of time. So let's get into a little bit of theory on the end mills itself. Now we go by, or you guys might go by our recommendations. Look at the catalog. For steel, for titanium, you have certain end mills. So you take it for granted that we design tools for that material. But there's our cases where, maybe you never know what the future brings, but there might be cases where you want to design your own tool because of something. Because of maybe a unique material that's coming from a foreign country or anything. So all these aspects of the flute, of the end mill, play an important part. Flutes, the helix angle, unequal helix at differential pitch, which helps with vibration. Core design, I got a nice thick core to handle long axial cut rake angles, depending on the material, which we'll learn here in a little bit. So through all these aspects of an end mill over here, design features, let's take a little closer look. When we design end mills, us and them, the less flutes it has, the smaller core is. It's allowing for bigger chip gullets to remove a lot of material, mainly for roughing. So maybe for sliding also, which you see 2 and 3 flutes a lot. But as you get bigger on bigger, but more flutes, the core gets much bigger. Now we're getting into maybe a finishing operation or high feed side milling. So you get more bending strength with more flutes, but you have less chip volume. It kind of goes hand in hand together, proportionate, right? So 2 flutes, you have large chip space. 3 flutes, chip space are almost as large as for 2. But when you go to 4, you don't have that much chip space, but you have that higher rigidity. So core, when you're choosing an end mill, make sure it's got the right core for the job. They come varying a little bit, more or less. The more flutes you have, the larger the core is. Depends on the application you're done. All right. Now, the helix angle square shoulder end mills, wide chip space, like I just talked about. You have a lot of room there for the chips evacuate. Slow helix, so you can sit there and you can rough out a lot of material. As you increase the helix, now you have very low radial forces. So you have less contact with the part radially, with the side of the part. All right. But what happens now is it's going to act like a corkscrew. It's going to want to pull out of the holder. And that's where you got to be able to lock it in some type of very good holder. Where it's a Weldon type, we've got a Weldon, the end mill has a Weldon flat. You might use some other ones that are out there. We have a collet to accommodate Weldon flats to go to Corachuk 930s. And when you go to 6-degree helix, very good surface finish because it has the least amount of contact with the end mill itself and reduced tool deflection. So for finishing, you see a lot of this over here. But there are tools out there, including ours, that do a very good job with a mediocre, not mediocre, but a medium pitch helix of 45 or 38 to 42 degrees. So keep this in mind as we go through over here. So helix angle effects on chip control, obviously with the 3-flute cutter, 45-degree contouring and 4-flute. Let's take a look at that. All right. Here we're just doing some, let's go entry into the part. You can see where the chip escapes from the part. When you're taking full slots, roughing applications, this might be a problem that the chips are coming up right behind the tool itself. If the coolant in it is not in the right spot, it could be recutting chips and everything. So you want something actually with a higher helix that will help throw the chips out. All right. Obviously this is a high-speed camera, you can look at that, but you'll see some of the other demos there. All right, so just for an example, helix angles, effects on cutting forces. All right, so we did a test with a straight flute drill. Right, straight flute drill, obviously all the forces are going at radially, right? But as you increase from 30 to 60, your forces are reduced radially, and that's the beauty behind high helix end mills. Or maybe if you're high feed side machining, you're using something between 30 and 42. But just to go an example, just to show you an example of this, how that works. So by increasing the helix angle, axial forces increases. Now I want to pull out. We got to make sure we hold on to end mill. I don't know if you guys have pulled end mills out of a holder. The materials I have to machine, they tend to come out. So I have to make sure I got the right holder going along with it. So I like to recommend the holders that we use to hold on to these end mills. I did see, if you guys ever see the verticals with maybe slots in them, the end mill pulled out of the holder, was still machining, but went through the part, and then it actually went into the, I have. All right, so unequal helix and differential pitch. Right? It plays a very important part as far as damping. You can just imagine if I sat there like a tuning fork in the same rhythm, you know, it's reverberating throughout my whole arm over here. But if I could just change the pitch of that just slightly, ever so much, and it actually contradicts itself, and it helps dampen the vibration or the minute vibrations that happen. And usually this would be about 2 degrees, and the helix angle will change from 38 to 42 degrees. So that all helps with surface finish, reduce vibration, and tool life. So as you cut through here, as you cut through that end mill, you can see that the helix angle changes. So what does that do for us? So with an equal helix angle in time and minutes trial versus unequal helix, hands down unequal helix paid off. Right? So you've did a lot of end mills these days, ours and theirs are unequal helix just for that benefit. Right. So core designs, there's several different core designs. One of the old end mills we have, it's still useful, is where you would use only the bottom part of the end mill, but you have to step down on a wall, so you still need some rigidity and you need some cutting length on that APMX for axial cut. So you would use the bottom end of the end mill to rough it out, and then go ahead and make a finished pass utilizing the whole length of the end mill. And usually about 90% of diameter is where that's at. Right? So now you'll be able to utilize it. But if you only utilize it for roughing, only the bottom end over here, and you're leaving this untouched, you're not utilizing that end mill like it's supposed to. Conical core, you'll see this in the long and reach applications, 4 and 5 times diameter, where your end mill's got to reach real far. Now you need something that's nice and balanced, and the conical core is what you need for that. So if you look at design something, say, hey, I want something with a conical core. And we have this tailor-made program, it's online also, and there's also obviously full specials, where, hey Hank, I like what you got, but maybe can we do this to it, and add a little bit more to it, and make some changes to make maybe an end mill that works for your material on your machine. So core diameter constantly increases from the face, the APMX, obviously improves chip flow, and it's a larger core at APMX. Maximum stability. Rake angles play a very important part. Gosh, if you have something, machining a tough machining material, tough machining application, you got real high helix, it's going to wear out a lot faster. It might cut a lot freer, but not for a very, very long time. So it's very important that we have the right helix angle for that. And obviously you use catalogs, and the recommendations are in the catalog. But sometimes, never know what the future brings you, that you will need to design something in the future. So rake angle has a direct impact on yielding angle of the chip and plastic strain, max temperature and temperature. The higher that rake angle is, the freer is going to be cut and less heat is going to happen, right? And I'm going to show you right here the rake angle effects on cutting forces first. I'll show you that a 0 degree versus, 10 degree versus 0 degree, and you can see there in the dark brown over there, obviously the cutting forces are a lot higher. And same thing in the radial and tangential over here. So hands down, it makes sense to go with something that's got the right rake angle on it. When the heat's generated, 0 rake angle, you'll see this in materials. We have to do hard milling, right? 60, 58 on up Rockwell, you know, it ain't gonna have a rake angle on it. If it does have a rake angle on it, it can last very long. What you need is something that's gonna hold up to that. So you see 0 to a positive rake angle on it to hold up to that. Basically, at that hardness, you plasticize the material. You melt the material in front of it in order to cut it. Right, so obviously, you see the heat zone over here versus that there. All right, so just a quick look at this, a rake angle overview. So anything less than 0 degrees should be using hardened materials, the ISO-H, or a class 60 or class 80 cast irons, which are really hard. You got a carbide in it, and then maybe some tool steels. Right? We use that. So as you increase the rake angle, we'll go ahead and add ISO-S, your Inconellos, your Hastelloids, even your titaniums, because you want to work hard on anything. You can just imagine what happens when you work hard on something. And then when you start getting a little higher in the rake angle over here, you can see we already added aluminum. Right? And then finally, with a very steep rake angle, you see a lot of aluminum angles out there with a very steep rake angle, and then that's where you can use those at. And along with some carbon 303 stainless or 302 stainless, very soft materials. So a little on that cylindrical, so here we have a cylindrical lamp. It acts like a wiper. It helps dampen and give you a better surface finish. Not all end mills have it. You might not want it for when you cut in stainless steels. because they'll tend to work harden, or your ISO-S materials like has like titanium. When they work harden, mount something sharp like this, but nothing that has vibra on it. But for steels, cast iron, that works out very, very well, plus it adds a reinforcement for the cutting edge. All right? Edge rounding depends on the material you're cutting and how sharp you want it. Obviously, a small edge treatment, or edge rounding, I should say, versus a large edge rounding. You can see there's a lot of heat built up with the very strong cutting there. Edge preparation toughness, you get a lot more toughness with a larger edge prep on the cutting edge versus smaller. And just a rule of thumb, ISOP, big and small, you could use anywhere. It depends if you're roughing and finishing. When you get into the work hardened materials like ISO M and S, you want small, you want something that cuts through. It's a perfect balance between feed, speed, and the cutting tool itself. All right. So corner preparation, very important as we go deep. Now we're going steep angles of 15, 20, 25 degrees, we're ramping down. So we need the right cutting edges for that. Sometimes you don't have time to take a drill and drill a hole, come in with your end mill and sit there and start interpolating the pocket. You know, maybe you want to use that end mill to go there to very steep ramp angles. The more flute you have, the less ramp angle you have available to you. I think I show you right over here. Let's talk about this here a little bit. One design for everything other than stainless steels, or this one is designed for stainless steels. All right. Sometimes you want to be able to. This is actually an old design where we want to. It's a quieter end mill. It grabs onto the tool, but you couldn't use the same tool as a finisher also, because these grooves were symmetrical and it'll leave a big line on that. So sometimes it depends on the accuracy of the part. You have to take a couple of cuts to remove those grooves. And these grooves are very, very deep. All right. So some of the machining methods. Let's go jump to machining methods now. We're going to talk a little bit about this over here too. I'm going to make sure. Oh, good. Okay. Plenty of time. Down milling versus up milling. I mean, this is the John. We talked a little bit about some of this over here too. When Klein milling don't work, then you go the other way, conventional milling. But it has its place. Carbide tools, they like compressive strength. You can take carbide, you can squeeze it, and you don't want to break it. As soon as you try to pull it apart, pulls apart very easily. We couldn't do it by hand. Maybe Dan Strom or whatever, he could probably do it, but it loves compressive strength, but it doesn't like when you have a cantilever type of action to it. So we always recommend down milling or Klein milling versus that. But you just imagine, if I start off very light, and I'm coming back out of the part like this over here, it wants to snap out of the material. And it's like it's like in a carbide. All right, so you have to be very aware of that. That's why we recommend this. Tool life with down milling, Klein milling is always much better, longer. But sometimes you have to do this. Ceramic tooling, you have to conventional mill. They want you to ease into the part because it can handle that cantilever forces that happen to a ceramic tool. But with carbide, no. The roll-in method. I mean, this has been around for years. All the software companies always had it. But remember, as I remember, switching over from cranking handles to NC tape machines to finally going to a CNC machine where when it enters a part, taking a full slot, I used to just slow down the speed. And once it gets engaged, then crank it back up again. Well, we've had this rolling method for years. The software companies always had it, but we just never really thought about it, at least I didn't. So rolling in allows a nice, easy entry. So it could be the same feed as you're going with the rest of the movement, but rolling it in is the best way to go. When you go to straighten the part, what happens, you have cutting forces both sides of that part, and that creates a lot of heat and a lot of vibration, and that either goes into the tool or into the part, right? And then that's when your tool life is going to suffer. To go straight into the part, you're entering on the thick part, you're exiting on the thick part. When you roll into the part, you're entering on the thick and exit on the thin. All right, so smooth entry, I say smooth. Keeps chips thin at exit, down is always recommended, reduces vibration, increases tool life. I mean, that's all we know these days, is for you younger folks. High feed face milling. Here's an application where you have to go deep. Maybe you're sticking out, your tool's sticking out very far. Like in John's case, he was talking about something earlier, he has to go very far, and you have, if you don't use the right tool, right type of high feed face milling tool, then you're going to have a lot of radial forces, and that's just going to bounce around like a pendulum. Speaking of pendulum, there's a face mill out there that we've made out of 3D printed, out of titanium. In some cases where you do have to use a square shoulder, you reach out very far, and if you have a steel face mill at the end of it, it acts like a pendulum, so it hits the part and bounces around, slow things down. But to have a lighter weight cutting tool at the very end, like a 3D printed titanium face mill, you don't have that pendulum effect. It bounces against the part itself. But a high-feed face mill comes in handy because you reach it in, and all the cutting forces are directed upwards. Some have 10 degrees, some have 15 degrees, some have 45 degrees. But the cutting forces are directed axially, therefore you're not bouncing around as much. So with a 10 degree, you'll have about 90% actual cutting forces and 10% radial cutting forces. So in some cases, you do remove a lot of material, especially those long reach applications. Short reach applications, you might not want to go that route, unless that's the only tool you have. Whether it's solid carbide or exchangeable head, or even an indexable style over here. They're built up on a couple of radiuses over here. Some of the indexable styles are a straight line, right? And that's how that works. What we're doing is we're utilizing chip thinning, which I'm going to talk about here a little bit. And chip thinning, or hex, is what we want to call it. It's the best thing for a tool. It makes it possible to run at high feed rate per tooth, maintain the correct hex. Let's get a little deeper into that. So normally here is our standard nose radius. But when we use a high-feed side milling, this chip thickness, that chip thickness is very important. It needs to run over the cutting edge and make a nice 6 and 9 over it. If your chip thickness is too shallow, it's just going to run into the cutting edge itself. It might want to try to cross over, and that creates heat and vibration. And that's going to wear out your tool a lot faster. So hex is very important. When you start dealing with high-feed side milling, that's where it's really important, or high-feed face milling. And that's the reason for that. So what you got to do in order to get that right hex thickness is increasing your feed rate. Trochoidal milling has been around a long time here too. You can use software for it, you can use some macros for it, but it's another method of utilizing the whole actual length of the end mill with very shallow radial cuts. It just goes in circles to create a slot. It is a slower method, but it is a predictable method, especially when you're, there you are, it's 3:30 at this shop. This big piece of Inconel has ran through several operations already, and it's getting close to quitting time, and the boss drops it off by you, hey, put a slot in it. So it costs $5,000 in material, it's already got $10,000 in labor costs, and all you gotta do is put the slot in there. So you're gonna sit there and try to power through it, take that chance? No, you're gonna sit there, take your time, and just go lightly over it, but very fast. And now that tool's gonna last long. Why? Because it's maintaining the same chip thickness, and you're using a less expensive tool, and less heat generated. So trochoidal milling has its place, and it's all available in all softwares we have available. Just in comparison, and this comparison here is actually faster because of the material. All right, so now I got 180% times diameter. My cycle time for 2 pieces is a minute. And in this case, it's faster, but it's an animation, so we'll take it for what that's worth. In some cases, it can be, especially when you stick it out very, very far. All right, so that's what that is. Been through the animation. The rule of thumb, we have this software to calculate everything out, whether you want to use an Excel spreadsheet or you have the programming software. We want to make sure that tool is no bigger than 70% of the diameter of the width of that slot itself. So max, and that's maximum of 70%. All right. So now you can utilize the whole actual length of that cut. You're going about your width of cut is about 20% of that the size of that tool. Now you sit there and use a trochoidal right through it. For long engagements, with deep pockets like this, that's a great way to utilize that. In some cases where maybe you have a light duty machine, you can't power through something. A high feed side machine, trochoidal milling, a slot like this is very, very handy. All right? So I've been talking about high feed side machine, but there's a lot of softwares out there that have their own versions out there. I don't know if there's any software people in here or anything. Nope. Okay. Peel milling is one of them. Dynamic milling. I think Mastercam's got that. GibbsCam is out there too. I think they use volume mill, which is right over here. But basically, it's high-feed side milling, maintaining a certain chip thickness, which I want to get into right now. You're utilizing the whole APM mix of that tool. Stop pointing there. So high feed side milling, radio chip fitting, what does that do for us? Obviously there's a calculation, but X is result of cutter engagement. So after 50%, there's no more chip fitting happening, but under 50%, there is. All right? There's calculators for that. Online on our tool guide, we offer that too, and the softwares are available here too. So depending on your AE or your width of cut, will depend on your feed rate and the way you have to increase it to get the right depth. There are tools designed for high feed side machining. They have around a 45-degree helix, 38 to 42 to be exact. You can do better chip evacuation because it's not pushing at a 30-degree angle out there. It's actually shooting up at 45 and it's shooting out at a real nice pace, especially if you're doing a full slap. The unequal helix, it's got the concept of high feed side milling and take advantage of the different grades. Most of the times you'll have a tough grade to handle long length. You can imagine if you had a very brittle grade, maybe a C1 or in our case be 1610, doing a long actual length of cut like that, any vibration will just pop that tool out. So you need something that's going to be able to hold on to it, be tough enough to handle that application. So radio chip fitting at 50% is whatever your feed rate, but once you move it to the side, you see how your chip gets very thin. So what you have to do is increase the feed rate to get the right chip thickness. We publish it, and I think maybe our competitors will publish too, the right hex that's required, chip thickness that's required. All right, so I'm going to rerun this video here one more time. So at 50% with the cut, no problem. It's whatever the feed rate is, but once you move to the left, you get if you kept the same feed rate, you wouldn't have the right hex. So you have to increase the feed rate to get that right hex. So like I said, so it rolls right over the cutting edge. Very important. All right. The recommended feed rate, driven by a recommended chip load for the tool. With a cut is dependent on that feed rate and then the surface feed is. So if a recommended feed rate and a chip load is all balanced together. So let's take a look at this video right over here. And the videos really help out as far as explaining things instead of reading to the left. It was supposed to move on me. I think you guys got an idea of what I'm trying to say. At 50% or greater, your feed rate is the chip thickness. But once you move to the left, reducing that with a cut, now you have to increase the feed rate in order to get the right chip to this, so that the chip can flow right across the cutting edge. All right, and what that helps out with, you're getting the heat into the chip, not into the tool or into the part. All right? Although your stainlesses, your ISO-S materials like Inconel, titanium, they don't like heat neither, so you're going to get some kind of, you got to find a balance between feed and speed for that. But you want all the chip to go into all the heat to go into the chip, and you know you got a good process. Because now you ain't getting no fluctuation, especially with a very thin part. All right, so what is high feed side machining? Traditional tool path is only used in the bottom end, the end mill, and it comes down, we want to use the whole thing there. We'll take a little closer look at that. Let's take a look at this. See if I can start from here. Can't start from there, let me start from here. Here is a 8mm end mill going 4 times diameter, so 32 millimeters deep. Got 10% width of cut, and just doing a shape. That's sticking out pretty far. I think this is also around 7 inches. The core chuck 930, hydraulic chuck. Run and dry, it's a piece of steel, 4140 is all it is. So, and there's other ways to skin that cat right. I could have plunged that material out and everything, but if I didn't have the machine strong enough to plunge the material out, or to use an indexable, I had to go to a solid carbide because maybe I had a DT30 machine. Well, this is where high feed side machining comes really, really in handy. So now we're to a point on a corner. If I went in with a big end mill, once it hit that bottom, what would it sound like? Like a big chirp, right? There it's chirping. So you go with a smaller diameter end mill, no larger than 70% of the diameter of the width of the tool, of the width of the groove, and you sit there and slice away at it. And you guys see this all the time. You know it works. For those who don't, it does definitely works. Now we're going to take this end mill as soon as it finishes a few more grooves over here. We're going to helical interpolate down to the bottom of the hole, and we're going to run around about 225 inches a minute. And we're going to dry it. In some cases, I should say in some cases, in a lot of cases, running steel and iron dry, you'll see up to 10 times better pay life. Don't drill dry. I mean, drilling, chips in drilling should be the same color as the material itself. Unlike turning and milling, you want the heat to go into the chip. So here we go, helically interpolating at a 3-degree ramp angle. Once you get down to the bottom, like I believe it's 225, And it just, it's not, camera doesn't speed up or anything, it's just utilizing that high feed side machine. So it'll make short work out of a block like that has a light duty machine, say. Slice it away in the corner. You imagine all the times that you heard chirping.
Your high feed mills are specifically designed to do that?
Yes.
Do I have to recalc the chip thinning, or are the numbers to them already taken into account? Because they're made for this, right?
Yes.
So the numbers that you spit out for feeds and speeds, is that already the numbers I should be using, or do I have to recalculate it out?
You'll recalculate out in your software. We give you the starting parameters because we don't know how far you're sticking out or the situation that you're in and all that. You go to Tool Guide online, the software, and they'll spit out the right feed rate for you. And just keep in mind, maybe through experience, that, well, I'm only holding on to the part by a little bit, and I'm going to take this big heavy cut. It might come flying out, you know. But we give you some place to start. We do spend time, right? As correct feed rates as possible. So here we went an 8mm end mill, going 32 millimeters deep, roughly 919 surface feet, 3-degree ramp angle. Right, so that's pretty impressive there for a small little end mill. Here the 2 times diameter end mill. It's 12mm, and we're taking a 10% on this side, and the other side we're taking a 70%. It's still utilizing a software. We're still maintaining the right width of cut, no matter where it is on the part itself. Obviously, we could take a drill or a plunge cutter or a big old cutter to do that, but we're not showcasing the indexable tools here. Just utilizing that. Sometimes it's a lot less expensive. You can see we were talking about going to a multi-edge, maybe a cutter that has 32, 40 inserts in it. You trash that. I mean, the cutter itself maybe $1,000, $1,500, and the inserts that go along with it, a couple boxes, there's something around $3,000. Maybe I just use this $100 end mill or $200 end mill and get the job done anyways, you know. I mean, it's an exaggeration of what I'm trying to do, but the point is, you go to a lot less expensive material tool. So let's go to the other side of that. There we go. So now we're taking a 70% width of cut. And no matter where it is on the part, it's always taking 70%. Maintain that same hex, same width of cut, that heat generation that's in there will give you the best tool life possible. And all the demos you see out there is utilizing all that. In some cases, we can run drive over there. Here, just plowing away. Because I can. It's a short projection, it's a short stout part, and it's very close to the table itself or that vise. So it depends. A high feed side machine has a place to go, but if you can high feed power mill, I would go with that too. It depends on the complexity of that part. Limitations of the machine, limitations of the fixturing, limitations of the part. All right, so no matter where I was on that part, I'm maintaining the same chip thickness. And that heat that's generated there, or no heat that's generated over there, is the same temperature all the time. Versus trying to gouge through a slot, or gouge through a corner or anything like that. And you get those different temperatures in heat, and that causes the carbide to expand and contract, and then prematurely wears. So no matter where I am on that part, it works out well. Why do we have to speed up the surface feed when we're high feed side milling? My contact of the tool, right, I'm only utilizing the 30%, 30 degrees of that 10% I'm using of the tool versus 50%, 180 degrees of the 50%. Well, we need to get that tool back into the cut as soon as possible. That's why surface feed will increase by 25 to 30%, even up to 100%. To get that, not only does it go into the cut, if it has time to cool off, you wouldn't think it has time to cool off, but it does, whether you're using coolant or not using coolant. You want to get back into the cut as soon as possible, maintain that certain temperature. If it has time to cool off, and again, you're going to have that thermal expansion of the carbide, and you'll lose tool life. You might not break the tool or anything, but what happens is that you won't get as many parts as you should on that end. So that's the theory behind increasing the feed rate. You'll see a big difference in that when you compare power milling versus high feed side milling. All right. What do we want to do? How do tools perform? We want to actually shear it. We want to plasticize the material. All right, maintaining that target hex. All right. Here we want to make sure that the heat is going into the chip itself. Right, cool tool temperature part is, so here, steel chips, the other one was stainless steel chips tend to turn yellow or brown, you might see. Make sure I ain't impeding on nobody else. All right, and then we got everything where we need to be as far as the tool goes. All right, benefit high-speed side machine keeps your tool in safe, optimal condition. Heat goes into the chip, like I've been bragging about here for the last 10 minutes. Reduces cycle time in most cases, depending on the complexity. And the hard to cut materials, titanium, Haskell, Inconel, 62 Rocco materials, it's the way to go. You have to high-speed side machine because you don't create that much heat and that much pressure. All right. Note a limited machine, proper tool work holding. I'm running out of time here, Jen, so I'm going to go a little faster. You got any questions? I'll be right out there too. Decide if we're going to high-speed side mill or we're going to power cut, air blast, chip evacuation. Sometimes they get better tool life running dry. And obviously get trained, like you guys get a little bit right there now. So high-speed side machine works great in smaller machines. The trend is going to smaller machines, using less power, less electricity, not so complex. So now you high-speed side machine because you're going light and fast and ain't that much tool pressure on the part. Metal removal rate, 10 times longer tool life. I wanted something to show you. So be aware of the actual cutting force. If you're going to think about anything, if you're doing it right now, you go to somebody else in that mill, you should have no problem. But going to the high helix, remember, it acts like a corkscrew. You want to pull it out of the tool holder itself. So be aware of that. Some way you got to captivate that end mill to keep them pulling out. And there's ways to do it. There's holders out there to do it, and right end mills do that. There's even the ILAC style too. That basically it's got looks like a worm thread that's in there. And 3D profiling. And am I running out of time here? Yep. Getting close. Yep. All right. So I got one more thing to show you. Profiling is another art in itself. I'll make sure these guys have enough time. Different process over here. You know, gents, we have all this online and everything, so I got to cut it short. Profile milling, you want to maybe use something with a larger radius so it doesn't have these stair steps when you do intermediate machining. All right. Flank milling is always better than point milling. Point milling, you have to rely on the tip of the tool, which you don't have enough RPM on the machine to utilize that. So flank milling, you use the outside diameter, peripheral diameter of the end mill, therefore you maintain surface footage. And to take away on this over here, when you do some profile milling, you want to make sure your feed rate and your step over is equivalent to each other. It's a lot easier for the people to polish things, whatever part you're making. Tool selections, the pull method versus this one over here. Obviously, pull method, bottom to the top, and push it from the bottom to the top, but you have a risk of it breaking down over here. And tool selection profile is very, very important, especially when your tool's going to be in a cut for a very long time. There's molds out there that are 90 hours into a cut. You want to make sure it lasts. You want to make sure if it doesn't last, the tool that you're going to replace it with has the same profile tolerance as the first tool. There's competitors out there that don't, and not that consistent as us. Make sure you got a good Matsuura machine to do some of the tools with, right? And then slicing away, we talked a little bit about that. You've seen that in some of the videos. And then the slicing away the corner. If you sit there, if you're trying to generate a radius with the same size of the tool, you're going to sit there, you have all this contact, and it's going to break and chirp and never. So you want to go with something smaller that might look like this. So you go ahead and slice away or interpolate it. Okay. And slicing summary, you don't want to sit there and gouge all the material out. You want to sit there and peck away at slicing away. And the ramping angles, different ramp angles. We recommend ramping angles. Obviously, you want to reduce some feed rate too. Only if the tool breaks, then you reduce it, right? But the 2-flute can ramp down a lot steeper than a 4-flute. But now with the new tool designs, we go to 15 to 20 to 25 degrees. I learned 25 degrees by accident, by the way. And there's plunge milling methods too. You plunge out material if you need to. True plunge milling tools. I think I have these guys set up too. Jim, I got to end it right here because I think they're out there waiting and everything. Folks, I appreciate you coming, stopping by. If you got any questions, I'll be right out over there. There's more videos I can show you and everything. Or go online for some of the training, all right? Thank you, everybody.
Thank you.
Appreciate it.